This lesson will cover Chapter 5, Section 5.1. In previous chapter, we talked about Ernest Rutherford and his experiment at the time. During his time, it was believed that the atom looked basically like this. This was the model of the atom. We basically had negatively charged particles scattered through a positively charged area. So the idea behind this was basically that if we took a if we took positively charged particles, such as alpha particles here, and we bombarded a thin foil sheet of gold with these positively charged particles, most of the positive should go straight through the negative without any resistance, but that's not what we saw. We saw that every so often we would get the positively charged particles, the alpha particles, to ricochet back. This led Rutherford to conclude that the model of the atom was more like this, where you had a center nucleus, which was positively charged, and basically you had electrons all around. So in conclusion, from Rutherford's gold foil experiment, led us to the understanding that atoms have a massive positive charged central nucleus. The nucleus is positively charged, and electrons are found outside. Where outside? We quite didn't know. It was just outside of the nucleus. The nucleus was massive and it was filled with positively charged particles. Questions left unanswered by Rutherford gold foil experiment. How are electrons arranged around the central nucleus? We didn't know that. Why don't electrons collide into the positively charged nucleus? That is, if electrons are negatively charged and opposites attract each other, why is it that the electron doesn't collide into the nucleus? And the next question left unanswered was why is it that certain elements have similar characteristics? Why is it that sodium is explosive, so is potassium, and they are within the same family? In order to answer these questions posed before, scientists during the 1900s made certain observations, and these were the observations they made. Elements emit a specific color of light when heated on a flame test. If you remember in class, we did the flame test, and you saw that different elements, such as, for example, copper, would give a color similar to this. And you saw lithium, strontium, and you saw the different colors. Different elements will give different colors. Now the question is, why is it that an element will give a specific flame color when heated? And they also realized that the behavior of elements seems to be related to the arrangement of their electrons outside of their nucleus. In questioning how electrons were arranged around the central nucleus of an atom, since we had no idea how these electrons were arranged around the nucleus of the atom, and scientists at the time believing that the electrons had something to do with the properties of the elements, and then also in noticing that different elements produce different color of light when heated over a flame test, they began to ponder about the wave nature of light. They realized that light travels in the form of a wave. Okay. Visible light is a type of electromagnetic radiation, and here we can see the electromagnetic spectrum. This is the electromagnetic spectrum that, as you can see here, this is the visible light. That is clear light, sunlight. And if you remember, and you've seen it in rainbows, when sunlight is passed through a prism, you see a rainbow of colors. Most of the time we call it Roy G. Biv, signifying red, orange, yellow, green, blue, indigo, and violet. And the spectrum is showing all of the different electromagnetic radiation. Visible light is a form of electromagnetic radiation. And we also have radio waves, we have microwaves, infrared, ultraviolet, X-ray, and gamma rays. All of these are electromagnetic radiation. Electromagnetic radiation is a form of energy that travels in the form of a wave. So electromagnetic radiation travels in the form of a wave. When studying a wave, there are certain aspects of the wave that we need to define and be clear on. First, there is the wavelength. The wavelength is the distance from crest to crest. The crest is the peak of the wave, or from trough to trough, which is the bottom of the wave. The center line is the origin, and we can measure amplitude, which is the distance from the origin to the top of the crest, or from the origin to the trough. Now, wavelength is symbolized by the Greek letter lambda, and wavelength can be measured in meters. It could be measured in centimeters. It could be measured in nanometers. So basically, the characteristics of the wave would be wavelength, distance between crest to crest or trough to trough, measured in meters, centimeters or nanometer, the amplitude, the distance between the origin of the wave and the top of the crest, and frequency is the number of waves that pass a given point per unit time. So if we are looking at a wave, we can look at a wave and we can measure the distance from crest to crest, being the frequency, the wavelength, or from trough to trough is also the wavelength. The frequency is the number of waves that pass a given point per unit time. Let's say we're measuring at this point, and this would be in a second. So it's the number of waves that pass a given point per unit time, and the shorter the wavelength, notice short wavelength will produce high frequency. Long wavelength will produce a low frequency. So wavelength and frequency are inversely proportional. If I have short wavelength, I'm going to have high frequency. If I have long wavelength, I'm going to have low frequency.